Welcome back to Inorganic Chemistry, where we're going to continue our discussion of acids and bases, and in particular we're going to look at Lewis acid or non-aqueous acids and bases. Last time we reviewed different models for acids and bases, and we looked at the properties of protonic acids. Now we're going to look at non-protonic acids, or acids not in, say, aqueous solution, and we'll spend time also looking at Lewis acids and bases. So, let's start out looking at another trend of protonic acids, and that is for metals in aqueous solution, they tend to be acidic. So this hydrated, so that's water around this metal center, say an iron atom that is octahedrally coordinated by water ligands, and this is say there's a positive 2 charge on the iron. Then in water it will dissociate to form the hydroxide ligand bound to the metal center, and then the rest of water is still there. So it gave off a proton. It was acting as an acid. So since one of the waters turned into hydroxide, hydroxide has a -1 charge, the iron has a +2, so the total charge on this complex would be +1. And the trend is that the acidity here is going to depend on the charge, and the size of the metal ion increases with the charge and decreases with the size. So you'd expect small, highly charged metal ions to be more acidic. And for example, the pKa of this is iron 2+ here, right? Iron 2+, and then we could compare that with the iron 3+. The pKa of iron 2+ is about 9.5, and we would expect iron 3+ is going to have more charge, and it's going to be slightly smaller, more compact ion, so that both factors should increase the acidity. In terms of the pKa of iron 3+ is around 3. Now let's look at the oxoacids of the nonmetals, and we're going to look at Pauling's rules to help explain their chemical behavior. And again, these are trends, and we'll see as we get more involved in the details that we might need to modify these a little bit. So the idea is that you have a nonmetal that is hydrated, a nonmetal oxide that's hydrated, and the degree to which it's protonated is distinguished here by a P or a Q, and then it will lose a proton to acting as an acid. So Pauling says that the important parameter here is the P value, or how many oxides are bonded to the central atom. So let's look as an example at phosphate. So phosphorus is in the center. We have an oxide and 3 OHs surrounding that phosphorus. So that means our P is 1, and then our Q is 3. So this is also an example of a polyprotic acid. We have 3 hydrogens here, and they all can be lost by this equilibrium. So Pauling would say that the pKa should be around 8 minus 5 times P. P is 1 for phosphorus. So 8 minus 5 times 1 is 3. And the pKa for this first hydrogen to come off of phosphoric acid is 2.1. So it's not quite 3, but again, this is an approximate trend. Now, the second part of Pauling's rules is that successive pKa values should increase by 5. In other words, if you have a polyprotic acid, like phosphoric acid, the second proton to come off should be that 3 that we started with, plus 5. It should be around 8. And the pKa of the second proton is actually 7.4. And then the third proton, again, should increase by another 5, so it should be around 13. And here you see the pKa of the third proton is 12.7. So now we're getting close to what we predict by these simple rules here. So you could also do this for sulfur or nitrogen or some other non-metal. Let's go. Now, I promised you that we would look at non-protic systems or non-aqueous systems. So let's look at the anhydrous oxides. And with anhydrous oxides, the nonmetals tend to form acids. So for example, if we put carbon and we make an oxide of that, say carbon dioxide, this is of course a gas, but if we react this with water, we can see that this is actually an acidic compound. So react this with water and we'll form H2CO3 or carbonic acid. You can see there's a proton there that could be removed and it will act as an acid. So that's a non-metal oxide. Metal oxides tend to form basic compounds. So for example, you could have calcium oxide, which is a solid. If you add this to water, then you're going to form calcium hydroxide. Which acts as a base in water, aqueous calcium hydroxide. So to do that, we had to take 2 hydrogens, 1 oxygen, so that's balanced. And that will form hydroxide in water, so that's a base. So you can see the periodic trend would be that metals are metallic oxides are bases, non-metallic oxides are acids. Now what about that region in between on the periodic table as you go across from metals to non-metals? There's that region where there's the metalloids. And these tend to form amphoteric oxides. Amphoteric means both. It's Greek. So a metalloid oxide will act as both an acid and a base. So let's look at an example of this. Say aluminum is a metalloid, so aluminum oxide or alumina, solid. React this with protons, so it's going to act as a base because it's going to absorb protons. If we add it to acidic water, then we will form, it'll dissolve and form a hydrated ion. Aluminum hexahydrate. So the alumina here is acting as a base because it's reacting with an acid. So that's base, basic. Well, what about acidic? Alumina can also react as an acid. Aluminum oxide solid plus base, aqueous base, and water, of course, to balance, will form a different type of complex, an aluminum hydroxide. Okay. So here it's acting as acid, so that's amphoterism. It reacts as both acid and a base. These ideas of the oxides without water acting as acids or bases is the Lux flood concept of acid-base chemistry. Now, what about the aqueous cations of the transition metals? So we talked about metals, nonmetals, metalloids, transition metals. Also need to talk about. And the trend here is that the higher the charge, the more acidic the compound will be. Also this way, going this way is more acidic. So this follows the same kind of trend as we saw before. So for example, let's consider vanadium. Right here, vanadium is, the vanadium oxide is basic, because if we react vanadium oxide with water, acidic water, it will form the compound vanadium with 6 hydrated waters around it. So this is a lot like the transition metal aqueous cations we saw before. This is going to act as acid, so this was a base to form that acid. And could balance this here. 3 of those. So we need 2 of those here. And then that leaves 1, 2, 3, 4, 5, 6, and 3 waters. Okay. So that's vanadium in the +2 oxidation state. What about in the 5 oxidation state? So we would say it should be more acidic. And actually, well, it's amphoteric. You have the vanadium oxide in aqueous solution when it's basic. And this is colorless. If you're in acidic solution, you have this compound, a hydrated vanadium oxide. So this is acidic solution, and this is a yellow color. And in between, and more neutral solution, the vanadium forms a decavanadate. So there's 10 vanadiums, 28 oxygens in this anion. And this is orange. So this is an example of a polyoxometallate. And it's also an example of how, depending on the pH, you have different color, and so the name of the element, vanadium, actually comes from all these different colors. And these are just a few examples of possible colors with vanadium complexes. And so vanadium, actually the name comes from the Scandinavian goddess of beauty called Vanadis. So we saw that once we get to pH 5, it's acidic. Okay. So we've seen some examples of different types of acids and bases and different definitions of acids and bases. So first let's review what we've seen so far. We saw that in water we had the Arrhenius Ostwald definition of an acid and base, which is one that forms hydrogens and hydrogen ions and hydroxide ion in water. And then if we divide up that water, we can define an acid and base in terms of what it does with a proton, or an acid and base in terms of what it does with an oxide. So the proton definition is the Bronsted-Lowry that we're most familiar with from general chemistry. And then the oxide definition is the one we just talked about, the Lux flood concept. Okay, a broader definition that still includes these ideas, that is what we're going to spend most of our time next talking about, and that's electron pair. That's the Lewis model, Lewis acid-base model. And then an even broader category would be to consider where the electron pair is coming from. It's coming from the donor-acceptor molecular orbitals, or the frontier molecular orbitals. Let's see if we can. So the lowest unoccupied molecular orbital would be the acceptor. The highest occupied molecular orbital would be the donor, and that is frontier molecular orbitals. And then there's even some people who have defined acids and bases in terms of just electron transfer, like single electron transfer, not pairs of electrons. So the single electron transfer definition comes from Yasinovich. And each of these definitions is a broader, more generalized example of the prior one. So Yasinovich can explain all of this chemistry, but we learn first Arrhenius Ostwald because it's the most simple to understand. Okay, so we've talked about these three types of acids and bases. Let's look at Lewis acids and bases now. And in Lewis acid-base theory, there's some vocabulary we need to learn based on reaction types. So one is adduct formation, or an addition reaction. So when you put an acid with a base, they come together to form a new compound, which is then the adduct, or the product, the adduct. You added the acid and the base together. So here the iodine is acting as an acid, and the iodide is a base. So iodide, if we look at the Lewis structure, which we do for Lewis acid-base theory, the iodide is going to donate a lone pair onto the iodine to make the triiodide adduct. Okay, single displacement is when you already have an adduct and you react it with either an acid or a base to displace part of the adduct to make a new adduct, product adduct. So in this case we're going to look at the base side. You're going to start with a base and react with the adduct. So for example, we can have diethyl ether, which is a base bonded to trifluoroboron, which is a Lewis acid, and then so that's the adduct, and we're going to react that with trimethylamine, which is a base. You see the lone pair there. So that lone pair will displace the oxygen's lone pair on the boron. So our new adduct looks like this. And our other product then is that diethyl ether, which is a Lewis base. Double displacement is when you have two adducts that react together to form two new adducts. So another definition of this is metathesis, or reordering, or it's like square dancing where you exchange partners. So for example, we have could have methyl mercury, which is highly toxic, bound to chloride, and hydrogen iodide, which actually is an adduct. And the hydrogen is, of course, an acid. Chloride is a base, so the hydrogen could displace the methyl mercury on the chloride to make hydrogen chloride, and methyl mercury would then combine with the remaining iodide to make the new other product. Okay, so how can we predict Lewis acid-base reactivity? So this is just defining the possible reactions. We can look at equilibrium constants. In this case, formation constant of the adduct. So we have acid plus a base to give the adduct. And here's some data that's been collected where the zinc is the acid, fluoride is the base, and that's the formation constant, or the log of the formation constant, to make the adduct. And so we see that the zinc as an acid versus mercury as an acid, we get different values, and actually we even get different trends. The fluoride starts out about the same reactivity, but then as we go down the group, the mercury equilibrium constant increases, whereas the zinc equilibrium constant decreases. It becomes less reactive. So then, say we have two adducts from these series of chemicals, so zinc fluoride and mercury iodide, and we want to know, is this going to do a double displacement? Are we going to make zinc iodide and mercury fluoride? So we know forming zinc fluoride is okay, but forming zinc iodide is weak. It's not favored. Forming mercury iodide is very favored. Forming mercury fluoride is not favored. So comparing these two possibilities, we see that zinc fluoride is more favored than zinc iodide. Mercury iodide is more favored than mercury fluoride, so we would predict, based on this set of data, that if we mix these adducts, that we would not actually get a reaction. So, how can we explain why these trends are the opposite? We have two acids, we have the same set of bases, and we get completely different trends. And this was explained by hard-soft acid-base theory, or HSAB. Hard-soft acid-base theory was proposed in the 60s, and the rule is that hard acids prefer hard bases. And the opposite is also true. Soft acids prefer soft bases. What is a hard or soft acid or base? Hardness is a property of an element or a compound that says that it is not readily polarized. So we've seen polarizability, and which is that the ability of the ion or molecule for the electron cloud to be polarized one side to the other when it's put in an electric field. So something that's hard would not readily be polarized. Another way to think about it is it holds its electrons tightly. So they're tightly bound to the ion or molecule, and so you put it in an external magnetic field and it doesn't change much. So there's a symbol for hardness, and it's based on periodic trends. It's the difference between ionization energy and electron affinity. So that's if we're looking at atoms or ions. If we're looking at molecules, we would look at the HOMO-LUMO gap, the highest occupied molecular orbital, the lowest unoccupied molecular orbital. If that gap is large, then the compound is considered hard. So if we go back to our previous data set, we see that the reason why this reaction is not favored is that we have hard acid, hard base, fluoride, periodic trend, we'd expect to be hard because it's the upper right part of the periodic table. Zinc is definitely going to be harder than mercury, which is lower on the periodic table. Iodide is lower on the periodic table, so it is soft. So hard is with hard, soft is with soft. So that is the idea behind hard-soft acid-base theory. So we would predict this is more stable than these are here. So you should be able to explain non-aqueous acids and base concepts, and define a Lewis acid-base reaction type, and also predict Lewis acid-base reactivity based on hard and soft acid-base theory.